Hello, my name's Tom Howard. I'm going to be talking about some aspects of changing UK coastal flood risk. I worked on the storm surge and tidal changes component of UKCP 18 Marine. UKCP 18 is the United Kingdom Climate Projections. It is the first major update since the previous edition, which was UKCP 09, and before that there was an edition in 2002, so roughly a 10-year cycle. UKCP 18 has these 6 different strands that we see here on the right. I'm going to talk about some aspects of the marine strand. The mission statement for the marine strand is to facilitate vulnerability assessments to aid coastal defence managers. I'm going to talk specifically about the extremes. The primary finding in terms of the extremes is that the mean sea level change is projected to dominate the change in the extremes. In the figure on the left, we can see the coastline of the UK mainland. The numbers indicate the location of tide gauges. These correspond to the numbers on the x-axis of the figures on the right. So in the right-hand panels, it's a bit like we have unwrapped the mainland coast clockwise, as shown by the red arrow. In all 3 panels, A, B and C on the right, we have the projected 21st century mean sea level change under RCP 8.5 shown by the green line. And the green shading shows the large uncertainty in the model projections. In panel A, the change in the 1-year return level of skew surge, as projected by 2 different climate models, is shown by the bars. In panel B, the bars show a single model projection of the change in significant wave height. In panel C, the bars show a simple metric of the projected change in tidal amplitude caused by the increase in water depth, according to a single model. The point of all these panels is to emphasize the dominance of the mean sea level change and its uncertainty. Given this dominance, I'll describe an approach to dealing with this uncertainty by combining it with the uncertainty which is inherent in the extremes. The Environment Agency allowances form the current government guidance for coastal flood risk assessments. These are location-specific allowances selected from the distribution of UKCP 18 projections of 21st century sea level change under RCP 8.5. The 2 levels selected for sensitivity testing are the 70th and 95th percentile. But I'm going to talk about a different application of UKCP 18 Marine, guiding the development of an alternative sea level rise allowance called Hunter's Allowance. This is not part of any government guidance. Rather, it was prepared in the hope of informing development of the next generation of guidance. Hunter's Allowance is an amount by which to raise defences in order to maintain the same expected frequency of flooding under a given probability distribution of mean sea level rise. To do that, it's not enough to raise the defences by the central estimate of mean sea level rise. I will describe why Hunter's Allowance is important and how it is evaluated. This is the return level curve of still water level at Newlyn in the southwest of the UK under present-day mean sea level based on current government guidance. And here in red we have the same curve with the addition of the central estimate of mean sea level change to 2100 under RCP 8.5 for this location. The faint red shading shows the 5 to 95 percentile range of the projections. RCP 2.6 is shown in blue. But I'm going to ignore scenario uncertainty from now on and focus on RCP 8.5. We already saw how the projected changes in surge, waves and tide are small compared to the projected change in mean sea level and its uncertainty. But here is a source of uncertainty which is not small compared to the projected changes. The crosses show the history of annual maximum skew surge at Newlyn from the tide gauge there. On the same scale, we have the central estimate of mean sea level change over the 21st century, shown by the green curve. The green bar shows the central estimate of the change averaged over the last decade of the 21st century, and the black line shows the uncertainty in that estimate. Typical projections of surge, wave and tide change at this location are also shown by the smaller bars. The point is that the annual variations in the maximum surge, shown by the crosses, are comparable to the uncertainty in the mean sea level change. Hunter's allowance combines these two sources of uncertainty, the uncertainty in the mean sea level rise projections and the uncertainty which is inherent in the annual maximum sea level. Hunter's allowance behaves a bit like the variance of the sea level rise projections divided by the spread of the extremes. I'll describe how it comes about now. Consider a typical extreme value distribution expressed as a return level plot. So this is the plot that we just saw for Newlyn. On the y-axis is the annual maximum water level, and on the x-axis is the average recurrence interval, sometimes called the return period. To simplify the explanation, I have assumed that the extremes follow a Gumbel distribution in this case. That gives a straight line return level plot. We can read off the so-called 100-year return level. This is the level which we expect to occur on average once every 100 years. We can also read off the 1-year return level. This is the level which we expect to occur on average once per year. Of course, this does not mean that it is guaranteed to occur every year. There will be some years with one occurrence, some with two or more, and some with none. Now let's change the way we label the x-axis. Instead of the average recurrence interval, let's label it with the expected number of exceedances per century. Like that. Now let's look at the effect on the return level curve of a single projection of mean sea level rise. If that's all we had, then our lives would be simpler. We would just raise the sea level wall by that amount in order to maintain the same level of protection as we have in the present day. Now let's look at a simplified illustration of the effect of uncertainty. Suppose that instead of a single projected change, we have two equally likely estimates. That is, we assign probability of 0.5 to each estimate. We can choose a level, let's call it Z star, and evaluate the expected number of exceedances per century under each of the two projections. 1 exceedance in the low case and 100 exceedances in the high case. Weighing each projection by its probability, we calculate the overall expected number of exceedances, about 50. "50 events per century, that's the 2-year return level. So there's our future 2-year return level with no uncertainty, and there it is with uncertainty. The dashed line shows the present-day return level curve. Here is how much we have to raise the defence to account for the central estimate of mean sea level rise. And here is the additional allowance for uncertainty. And it turns out that if our return level curve is straight, and because of the properties of the log scale, then this allowance is the same for any return period. This is Hunter's allowance. It's an objective method for dealing with mean sea level rise uncertainty once the distribution of mean sea level rise has been specified. It maintains the expected number of flood events in the face of uncertainty in mean sea level rise. Alternatively, by referring back to the return level curve, Hunter's allowance can be reinterpreted as a multiplication factor in the frequency of extreme events if no intervention is taken. If the return level curve is straight, then the same factor applies to all return levels.